Everyone settle down, please. We're gonna go through this paper in your problem of the day. Now, remember the other free body diagrams that we've looked at, the box is all that you need for the picture, right? I mean, you can put extra stuff in there if you like, yes. Just do fast. If you, if you do extra stuff, that's fine, but just make sure that that core box is staying the same, all right? That way we have one thing to compare to each other. Now, we're also going to do our best to identify these forces and include them in the drawings, right? So the forces that we put in there, remember, you should put those types with it. The first one is a physics books rest upon a level table. Okay, who's got a good answer for this? All right, Kale, what do you think?
I had gravity going down.
Okay, good.
And then I don't know what's going on.
Okay, now, if there was just this, what would happen with the book? It would be falling, right? Okay, so we need to have a force that opposes gravity. If we don't have the force that opposes gravity, then it's going to keep falling. The name of that force is the normal force. Okay? And that's going up. Yes?
Can't you do like the arrows switch?
Yes.
Can't you do like an arrow going down on the top saying gravity?
You could. That's fine. As long as you always have whatever you consider to be down to be gravity, because unless you're operating in a place that doesn't have gravity, you're always going to have that force acting on it. So if that body is not moving down or up, then the normal force also has to be there. Okay? Unless it's air resistance, but we'll get to that later. All right? So the normal force is always if you have a body that is sitting on top of, let's say this case right here, sitting on top of this S, you have the force that's going down, which is gravity, so then you have to have an opposite force going up, which is the normal force. It's always perpendicular to the surface of the object. All right? And that's the normal force. It's not a big deal. It makes a lot of good logical sense. Right? If we don't have that normal force there, then things fall. But eventually it'll have the normal force, right? Hits the ground and stops. Falls down in the pit and stops. As soon as it stops, the normal force is there. All right? Okay. Let's see here. All right, Lauren. What about our little skydiver here? Ooh, that's a new term, right? Terminal velocity. Anybody know what terminal velocity means? Yes. Like it. Now, this is something that happens when objects fall. Is if there was no air around, they would just keep accelerating all the way until they hit the ground. But because of air resistance, there's a maximum speed that things can go. Right? So like if you go to the top of the Empire State Building and drop a penny, don't do that. It's really dangerous. But if you did, it would, at some point, you would hit the maximum speed and would not get any faster until it hits the ground. That's called terminal velocity. Right? It's still really fast, really dangerous. Obviously, if you jump out of an airplane, you don't have a parachute, you're going to die. Terminal velocity is enough to make that happen. All right? It's enough to make that happen, but there is a maximum speed there. Okay. Now, but let's go back to this. What forces are going to be involved here? Yes? Go ahead. What, Lauren? I'm sorry. For sure, you have gravity. Oops, that's terrible. Okay. And then what else? There you go. Right? Now, what's going to be true about the force of gravity and the force of air resistance? Yeah.
Gravity's gonna be stronger.
Careful. If it's terminal velocity and it's one speed, it's a constant speed, what does that mean? They're the same. Okay? It's still falling because it was already falling when it hit the equilibrium point between those two forces, but it's not speeding up and it's not slowing down, so then the forces must be the same. And it's really important for you to make sure that you understand if something stays at a constant speed, then the forces are balanced. Okay? Everybody got that? Okay. All right, a large crate is being pushed leftward at a constant velocity. Those important words again. Okay. So, what do you guys think about this? What do you think, Jack?
Friction is on the right and application force is on the left.
Good. Okay. And we would say those are probably roughly the same. Okay. Now, let's make sure that we define those. What is friction? Yes. Right. And when does friction happen? What makes it happen? Right. You go like this, right? This is friction. What happens? Your hands get warmer, right? Because you lose energy to friction, right? And you don't really lose it. What happens is some of the energy for the movement gets transferred into heat energy. And the heat energy is what warms up your hands, right? So you lose some of it because of that. But the point is, the friction is, yes, exactly. It's something that opposes motion, and it's because two objects are coming in contact with one another. Right, now, understand that air resistance is the same thing as friction. It's just a special case of friction. Because as you're going through the air, what happens? Think of the terminal velocity thing. What happens between the air and the body that's going through it? All those molecules are hitting it, right? The air molecules are hitting up against the body that's going through it, which is slowing it down, and then eventually it equals out. So anytime, or like you're running, and it's harder to run with a headwind going into you, you're losing some of your energy to that friction, right? That's all it is. So, yeah, here you're going to have those balanced. You know, if you want to be fancy, you could put the normal force up and down. Usually not a huge deal, but it's just more thorough. Sorry. Okay. Questions on that? Everybody got it? Okay. All right, Mr. Hensley, what about D here? A sledder has reached the bottom of a hill and is coasting rightward while slowing down. Now, I wasn't very nice to Mr. Hensley because this is a little bit more of a complex one. We have to think about it a little bit, but that's okay. He can handle it.
Gravity going down.
Okay, good.
Could be friction going up.
Not going up. Think about going down the hill, right? And it's coasting rightward, right? So it's moving this way. So, well, which way does friction help the motion or hurt it? Right, so it's going to go against it. So friction is always going to go against the motion. So it's going to have to go to the left. And this will be friction. Okay. And technically speaking, since it's at the bottom, we would have the normal force there. Okay. Now, since it's slowing down, that tells you that there's no more force to the right. If there was a force to the right, like if somebody, like, you know, you have your sister or something at the bottom of the hill and she comes up and she starts pushing you, you're not going to slow down so much. Right? But if you're just slowing down, then there's no more push in the direction that you're going. All the push is against your motion, and that's why eventually you're going to stop. No matter how fast you were going down that hill. And even on snow, you're going to get some friction, right? It's not as much as it. That's why we can't just go out right now with our sleds and go sliding down hills, because there's way too much friction. And we could, probably not any much fun, but we just got to bounce around down the hills. But when it snows on there, that's what happens, is it reduces the amount of friction, and therefore, that's why, like, you don't really always want to sled right at the beginning when nobody's sled yet, because there's still a little bit too much friction, and you're not going to go as fast. Well, then once people go and jam down the snow, and there's less friction on the surface and it's smoother, that's when you really go fast, right? And obviously, the best case scenario would be pure ice, although it's probably dangerous. Don't do that. But you would go the fastest in that scenario. But that also brings up another point about friction isn't always bad, right? We wouldn't want to have no friction on the floors when we walk. Or it'd be like walking on big things of ice all the time, right? You're falling down, there's no way we could do it all the time without having something to make friction, right? People sometimes get like chains and stuff to put on their tires that's really, really slippery out. To give them a little bit more friction and break into the ice rather than just slide on the surface. So friction's not bad or good. It just depends on the situation. All right. Anywho. All right, Daniel. E.
Up is FAPP.
Good. And then what's going down?
Gravity.
Good. Now, you may or may not have thought of the FAPP, the application force, but if you take a look at any projectile, like if I'm going to throw this up in the air and it's sitting here on the table, is this ever going to go up without me doing something? You have to apply a force when gravity is present in order for anything to go up. So if the object is going up, at some point, there had to be some force pushing it upwards. You can't just go up on its own. You can't oppose gravity without another force. So if the ball's moving upward, it has to have an application force, and because it's moving upward, it's still beating that gravity. So the force had to be greater than gravity. Eventually the tides will turn, but more on that in another unit. All right. Okay. So, Mr. Tidwell, what do you think about letter F?
I put F grav going down.
Okay.
F air going to the left.
Okay.
And I put F norm going to the right, but I don't think that's right.
You remember, you always want F normal always be, if it's present, will always be opposite of gravity. Wherever your gravity is going, the opposite side of that will be the norm. So this is not balanced, right? But should this be balanced? Should this be balanced forces? What tells you that it should be balanced forces? Yeah. Constant speed. Okay? That tells you that it's going to keep doing whatever it's doing. That tells you that there's a balanced force acting on it. So, we could put like an application force maybe going to the right. But it would be, roughly speaking, the same as whatever is pushing it to the left. Okay. Questions on that? All right. About halfway down here. The brakes are applied to a rightward moving car, and it skids to a stop. All right. So we don't have any up and down. So before I even call anyone, you can put these in there. Gravity. F. Oh. Okay. Now, which way then are we going to put the brakes? To the left, right? Because of cars moving rightward. So when you put the brakes on in your car, whichever way you're going, it goes the opposite direction. The force is going in the opposite direction because your car's going this way and it wants you to stop. So in order to counterbalance it, it has to push you this way. All right. So how did brakes work with the pads that come together? So we say that brakes work with friction. So when brakes are present, you can just use the force of friction going against the motion. If you put like F brakes, then that, I'm not going to lose sleep over that. But technically speaking, this is from friction. Okay. Now, here's an important question, especially for you drivers. When you're hitting the brakes, do you have the gas pedal on at the same time? No, hopefully not. I mean, I guess you could, but hopefully you don't. So there's no more force going to the right, right? Because when you hit the gas, that's what it does, is pushes it forward, and then this means right is forward. So either you're on the gas or you're on the brakes. You typically are speaking, you're not going to be on both. So if the car is slowing down, then the force that was pushing it forward previously is no longer there. Okay? Yes?
I thought all cars, the engine started, you always have a force like 10 miles an hour.
That is true. So if you wanted to put a little tiny one there, I wouldn't lose sleep over it. But it's not going to be anywhere near the amount of force from the force of friction. So, but I mean, technically speaking, yes, that's true. All right. And you know that because as soon as you take the brake off, like you stop, you start to go forward again. But that's just the design of the car. All right. Okay. All right, Mr. Hanavan. Since H and Hanavan go together, tell me about the spider.
You have a force of gravity going down, but you also have a, you have a friction force.
Yeah, I kind of like that. Yeah, I'll go with that. And then they're going to be roughly the same. Why are they going to be the same? Constant speed, yes. If you don't have a change in speed, you don't have a force, whether it's slowing down or speeding up. All right. Okay. Oh, let's see here. Have we gotten Ellie yet?
Me?
Okay. Well, let's talk about Ellie here. What do you think about this projectile? All right. We'll say, got a volleyball serve going upwards and rightwards over the net.
There would be air going, like the air going towards the right.
So when you serve the volleyball, are you?
Or forward or upwards with the air going upwards.
Well, if you're hitting the ball, which way is air going to be working against it? The opposite way, right? So if you hit it to the right, to the left, yeah?
Yeah.
Okay. Okay, F air. So then your application force will be And then what's working down?
Gravity.
Good. Okay. Now, this one you got to be careful about because, like if I'm going to throw a projectile here to Jack, I have to throw it both up and at him, right? So you're actually going to have two application forces here. Because you have to use some of the force to go up as well as some of the force to go to the right. All right, there's two components to that. All right, and if you see someone serve a volleyball, they don't serve it straight ahead. You serve it up, right? And that's kind of the art of it is to swing your arm in a way that is as right as to go over the net as fast as you can, but also have enough of an arc to get over the net. Guess we lost our time. It's okay. Okay, so then upwards is also F-app. All right? Questions on that? All right, let's tell you what, I want to make sure you guys have enough time. We'll go over the other three when you